Consider the graph of f of x equals 1 over x minus 2. This function is obtained from the function g of x equals 1 over x by a shift on the input variable. Accordingly, the graph of f is obtained from the graph of g, which is a hyperbola, by a shift to the right of 2 units. The vertical line at x equals 2 is called a vertical asymptote of f. It's a vertical line that's approached by the graph of f as x goes to 2, either from the left or from the right. From this graph, it's clear that the limit of f as x approaches 2 from the right is equal to infinity, and the limit as x approaches 2 from the left is equal to minus infinity. These one-sided limits are also evident from direct numerical analysis. For example, let's look at the left-hand limit. For this limit, x is to be thought of as being very close to 2, but to the left of 2. For such x, the factor of x minus 2 is negative, because x is smaller than 2. As x approaches 2, this factor becomes closer and closer to 0, meaning that it becomes a very small negative number. The fact that this very small negative number appears as the denominator of f of x means that the overall fraction of f of x will become a very large negative number. This means that the limit from the left will tend to minus infinity. The right-hand limit, on the other hand, will be positive infinity, because in that case we're taking x to the right of 2, and so the denominator is a very small positive number, which causes the fraction to blow up to positive infinity. Because positive infinity is not the same as negative infinity, the full limit of f of x at x equals 2 does not exist. However, there are functions where the full limit is infinity or minus infinity. For example, consider the function f of x equals x minus 2 over x minus 5 squared. As in the previous example, we could investigate the behavior of f by drawing a graph, but this function is a little bit more complicated, involving x in both the numerator and the denominator. So instead, let's think algebraically or numerically. We'd like to know whether this function has any vertical asymptotes, and, if it does, what the limiting behavior is at these asymptotes. For a rational function like this one, good candidates for vertical asymptotes are those values of x that make the denominator vanish, because at those points, it's often the case that the fraction blows up. For this function, this means that x equals 5 is a good candidate for a vertical asymptote. To check this, let's look at the right-hand limit and left-hand limit at x equals 5. For the right-hand limit, we're supposed to be thinking of x as being just a little larger than 5, which makes the denominator a very small positive number. On the other hand, the numerator is tending to 3 as x goes to 5. So, what we have then is that this function is tending to a fraction that is similar to 3 over a very small positive number. In fact, the positive number in the denominator can be made as small as we'd like, so this means that the full quotient should blow up to plus infinity in the limit. For the left-hand limit, we're supposed to be thinking of x as being just a little smaller than 5, which makes the factor of x minus 5 in the denominator negative in this case. But since this number is being squared, this means that the overall denominator becomes a very small positive number. For similar reasons to as before then, the left-hand limit is equal to plus infinity as well. Because this left-hand limit agrees with the right-hand one, the full limit is said to be equal to plus infinity as well. What this means then is that the graph of f contains a vertical asymptote at the line x equals 5, and the values of f tend to plus infinity from both the left and the right. It's important to be a little bit careful when investigating the existence of vertical asymptotes, because not all roots of the denominator lead to vertical asymptotes. For example, consider this rational function. The point x equals 1 is a root of the denominator, but it's also a root of the numerator, so in the limit as x goes to 1, we can actually reduce by this common factor of x minus 1 to find that the limit is equivalent to the limit of x minus 3 over x plus 1. Taking x to 1 then, we see that this limit is equal to minus 1, which is a finite number. This means that the line x equals 1 is not a vertical asymptote for the function, even though it's a root of the denominator. Instead, you can check that this value of x equals 1 is just a place where the graph has a hole. Other functions which have vertical asymptotes include trig functions. For example, it's well known that tangent of x has an infinite number of vertical asymptotes, as seen from its graph.